All right, in this video, we're looking at the topic of alkenes and alkynes, two of the major groups of hydrocarbons in the organic chemistry unit for advanced grade 11 chemistry. Most of what we're going to talk about today also applies to the regular grade 11 chemistry class, but we will talk a little bit about cis-trans geometric isomerism, which is not something that the regular classes need to worry about. So organic chemistry, we've already talked about alkanes, normal and branched alkanes, and we've discussed cycloalkanes. So if you have your worksheets in front of you, let's look at them together. So question 1 says, we're going to fill in the blanks. Blank hydrocarbons include both alkanes and these, which have only carbon-carbon single bonds. As you do the video with me, pause and try it yourself rather than just copying my answers. So this is talking about molecules with only single bonds. So the best word for that first blank would be saturated. Saturated hydrocarbons have only single bonds between the carbon atoms, and as a result, they have the maximum amount of hydrogen atoms attached. So the next sentence, they have the maximum amount of hydrogen atoms in the molecule. There's two kinds of saturated alkanes. The simplest are the basic alkanes, the molecules which are just chains of carbon atoms with branches on them. But you can also have cycloalkanes. These are the alkanes that are joined to make rings. So alkanes and cycloalkanes would be the two types of saturated hydrocarbons. Well, in today's video, we're going to talk about molecules that don't just have single bonds between carbon atoms. Instead of being saturated, these are going to be called unsaturated because they're going to have fewer than the maximum amount of hydrogen atoms. They're going to have carbon-carbon double bonds and carbon-carbon triple bonds. In the case of double bonds, if there is one or more double bond in the molecule, then that molecule is going to be referred to as an alkene. Notice the ending ene. The molecules which have triple bonds in them are going to be referred to as alkynes. So an alkyne, and notice its ending yne. When you name an alkene, its name will end in ene. For example, the simplest alkene would have two carbons. You have to have two carbons in order to have a carbon-carbon bond. It'll have a double bond to be an alkene, and then two hydrogens on the first carbon, two hydrogens on the second carbon. Its name would just be ethene. Its formula, C2H4. Notice something very important about that formula. When we talked about alkanes, the general formula of an alkane was CnH2n plus 2. That was for alkanes. So if you had 4 carbons, you would have 10 hydrogens, 2 times 4 plus 2. To form a double bond between two carbons, you can only do that if you take away 2 hydrogen atoms. So now, instead of a formula CnH2n plus 2, an alkene will just be CnH2n. We have to remove 2 hydrogens, so instead of 2n plus 2, it's just 2n. And you can see that in this example that we've just seen, 2 carbons has 4 hydrogens with it. The simplest alkyne would have 2 carbons also, but now it's going to have a triple bond between them, and that means each carbon ends up getting just 1 hydrogen atom. Notice its formula, C2H2. How can we rationalize that formula? Well, now that we have a triple bond, there are 2 extra bonds compared to an alkane. For every extra bond, we lose 2 hydrogen atoms. So for an alkyne, the formula, instead of 2n plus 2, will be CnH2n minus 2. We lose 4 hydrogens, so 2n plus 2 becomes 2n minus 2. And you can see that in this example. 2 carbons, if we times that by 2, we'd get 4. Subtract 2, and we get 2 hydrogens. The name of that molecule, because it has the triple bond with 2 carbons, is going to be ethine. Okay, so you notice alkenes, their names end in -ene, while alkynes, their name ends in -ine. In these examples, there was only 2 carbons, which meant there was only 1 bond in the molecules. If there's only 1 bond, or even if there were 2 bonds, then we don't really need to say which bond is the double or which bond is the triple bond. But when you have 3 or more bonds in the molecule, we're going to have to include a number in the name to tell us which bond is the double or triple bond. We'll see that in just a moment. Now, the next paragraph in this fill in the blanks is really a little bit of an application of organic chemistry to oil refining. When you drill for oil, the crude oil that comes out of the ground is a complex mixture of hydrocarbons, some of them quite small and some of them very, very big molecules. The first thing you would do after you have drilled for the crude oil is distill it. You'd put it through a distillation process. The smallest molecules would have the weakest intermolecular forces, the lowest boiling points. They would boil and come out first. Then as you continued to heat, the next molecules with slightly higher boiling points would come out. And then as you keep heating, you're extracting different hydrocarbons based on their boiling points. When you're done, at those last fractions of your process, you have some molecules that are huge, and those are not very useful for many applications. So in this paragraph, we're going to talk about what they do with some of those really large molecules that they get from refining the oil. The large molecules are heated to very high temperatures. You're going to read a little bit more about this later in the handout. And also, they're put under very high pressures. When they do that, the molecules break. So those very large molecules break into smaller ones. One of the products is always ethene. That's that molecule we saw up above, C2H4. And then you get smaller alkane molecules as well. This process of breaking the large molecules with heat and high pressure is called thermal cracking. You take large molecules and under high temperature and pressure, crack them or break them apart into smaller molecules. You can also do the process at lower pressures and temperatures, but for that you have to add a catalyst, which speeds up the process and makes it possible to do under more normal conditions. The problem is catalysts can be quite expensive sometimes, so it might in the end be cheaper to do it at a high temperature and pressure. Again, you're going to read more about this in later paragraphs in this section of the booklet. In question 2, we're going to look at some examples. These are mostly bond line formulas, a little bit of a hybrid bond line formula because some carbons are shown. We're going to come up with the name and formula of some of these molecules. Let's do the first 2. In the first one, we see a 3-carbon molecule, 1, 2, 3. And we notice it has a double bond. So in my head, the first thing I'm thinking about is propane, because I see 3 carbons. But noticing that it has a double bond makes me realize that the ending should be propene. Alkenes have double bonds. Now, looking at that molecule, if we start at the end closest to the double bond, we notice that the bond that is the double bond is the first bond in the molecule. Now, should I tell you that in the name? Do I have to tell you that it's the first bond that's the double bond? Or is it clear? Well, consider if the bond that were the double bond had been this bond instead. Well, if that had been the double bond, we would have started numbering there, and it would still have been referred to as the first bond in the molecule. So because there's only 2 bonds in this molecule, whichever bond turned out to be the double bond would have been the first bond in the molecule. So therefore, there's no need to number it. Calling it propene is sufficient. Look at the second example, and things are a little bit more complicated. The parent chain has 1, 2, 3, 4, 5 carbons in it. We see it's a double bond, so there's an alkene. This is an alkene with 5 carbons, so the name pentene comes to mind. But we notice that you could put this double bond in more than one place. In this example, it's the first bond in the molecule, but it could have been the second bond in the molecule, and that would have been a different position. It could also have been the third, but wait, if it were the third bond, we would have to start numbering from the other end, closest to that, and in the third bond's case, it would revert back to the second bond, because we'd count from the other end. So in this case, there's really just 2 places the bond could have been. The double bond could be the first, like it is here, or it could be the second bond in the molecule. In that situation, when there's more than one possible location, you have to tell me which bond is the double bond. There's 2 ways to do that. The American way of doing it is to say 1 pentene. They're saying 1 because the first bond was the double bond, and they put the 1 out front like that. The UPAC way of doing it, UPAC, this is the organization that gives us the rules for naming, they prefer to do it in a slightly different way. They'll say pent, and then they put a dash, a 1, another dash, and then ene, and you would say pent 1-ene. That's actually how I prefer to do it. So if you're in this booklet, I'd prefer that we use the UPAC system of naming, but you will see me occasionally use the American system because it's very common. Okay? We use American books, so we're going to see that quite a bit. Look at the third molecule. We see a double bond in it, which tells us this is an alkene. We don't see any branches, so just count your carbons. There's 1, 2, 3, 4, 5, 6, 7 carbons. We're going to count from the right-hand side because that's closer to the double bond, and we notice the second bond is the double bond. So with 7 carbons, heptane comes to mind. It's an alkene, so heptene is going to be the actual name. An American would call it 2-heptene, but according to UPAC rules, we'll say hept 2-ene. Now, all of the molecules we've seen so far had no branches. They were just straight chains of carbon atoms. What are their formulas? Well, the first one had 3 carbons, so C3. It has only hydrogens in it as well, so H something. We remember that for an alkene, the formula that we derived earlier was CnH2n. So if you have 3 carbons, you're going to have 6 hydrogens. In the second molecule, we see 5 carbons, so C5, and therefore we double that. It's going to have 10 hydrogens. In the third molecule, we see 7 carbons. We double that. It's going to be C7H14. What about part D? Well, part D, we can see it has a branch. Okay, so let's carefully find the parent chain. 1, 2, 3, 4, 5, 6. So it's got 6 carbons in the parent chain, the longest continuous chain in the molecule. We see a double bond, and we notice it's the second bond if we count from the left, counting from the end closest to the double bond. And we see that there's a branch. That branch is a methyl branch. Now, which carbon is it on? Well, the double bond determined which end we should count from. We're counting from the left because it was closest to the double bond. If we count carbon atoms, let me use a different color for that. The carbon atoms, this is carbon 1, carbon 2, carbon 3, carbon 4. So the branch is on the 4th carbon in the molecule. So therefore, this name would be 4-methyl. That's a methyl branch. And then with 6 carbons, we'd say hex. And it was the second bond that was the double bond. So hex 2-ene. What's its chemical formula? Well, hexene has 6 carbons. The methyl branch is an extra carbon, so C7, and then H14. Notice that this formula is the same as the last formula, but these two molecules were different. So these two molecules, I'll use a different color again, these two different molecules would be referred to as structural isomers. They're isomers because they're different molecules that have the same formula. They're structural isomers because they're different in the way they're connected. The molecules have the same number of carbons, but they're not connected in the same ways. The carbons are connected in 2 different ways. So therefore they're structural isomers. I'm going to let you do a few on your own, but let's do part H together. We'll finish with this one in this question. We start with the parent chain, the longest chain, 1, 2, 3, 4, 5, 6, 7, 8. That's one way to do it. It's possible, theoretically, that the double bond or even the triple bond could be in a branch, that the parent chain is not where the double or triple bond is. That's possible. But that gets more complicated. So in this quick unit on organic chemistry, we won't see that. So for us, the parent chain will always contain the double or triple bond. But remember, the parent chain has to be the longest continuous chain in the molecule. But for us, it will contain the double or triple bond also. So in this case, there's 1, 2, 3, 4, 5, 6, 7, 8 carbons in this longest parent chain, and the double bond, which makes it an alkene, is the third bond if we count from the left. We count from the left because that's the end closest to that double bond. We also notice, again, I'll use a different color, that there are branches. Counting from the same side, from the left, there's a branch on carbon 2, and we can see that's a methyl branch. 3, 4, 5 also has a methyl branch. And on carbon 6, we see a 2-carbon branch, which is an ethyl branch. So we remember when you have different types of branches, you name them alphabetically. So ethyl comes before methyl. So therefore, we're going to call this 6-ethyl. And then 2, 5. Now remember, we have 2 methyl branches, so we use a prefix, dimethyl, Don't just say methyl, you have to say dimethyl. And then it was an 8-carbon chain, but it's an alkene with the double bond as the third bond. So with 8 carbons, we'll say oct, and then the third bond, so 3-ene. Ene because it's an alkene. Now, just a quick reminder, when you're putting branches alphabetically, you don't use the prefixes to alphabetize. So we put, oops, I meant to grab a highlighter. We put ethyl first because E comes before M in methyl. We don't look at the D in dimethyl when we're putting the branches alphabetically. What's this guy's chemical formula? Well, 8 carbons are in octene. 2 methyls would be 10 carbons total. And then that ethyl would give me 2 more. So this has 12 carbons. There's only hydrogens attached. I notice the double bond, so it's going to be C12H24. Okay, I'll leave question 3 for you. I'll leave question 4 for you. Let's take a look at question 5. We'll now draw some molecules. It says draw the condensed structural formula. For the sake of time, I'm going to change that and just draw the bond line formulas. They're a little bit faster and easier. So for part A, we notice that it's an American way of saying it. We see 2-pentene. That's the American way of doing it. It has 5 carbons, pentene, in the parent chain. The ene is telling me there's a double bond, and the 2 is telling me it's the second bond in that 5-carbon chain. So when I draw them, I always draw the double bond first. So there's my double bond. Then I say to myself, it has to be the second bond in a 5-carbon chain. So if I put this, there's carbon 1, carbon 2, carbon 3. I need 2 more carbons. So I'll do this and I'll do this. There's 5 carbons in a row, and the second bond is the double bond. So that's 2-pentene. Carbon 3 has a methyl branch. Numbering from the same end, from the left, carbon 3 has a methyl branch. There's my molecule. Now I'm ignoring as I draw this, and in the name it wasn't specified, there can be, and in this particular molecule there would be, some geometric isomerism, where we use cis and trans as part of the name. In this question, we're not going to look at that. For part B, 2,5-dimethyl, 3-hexene. So again, I see the hexene, E-N-E, tells me it's an alkene. There's a double bond. So I'll start with that. There's 6 carbons in the parent chain, hexene. The third bond is the double bond. So let me start by trying to draw that. Boom, boom. So right there, I've got 1, 2, 3, 4 carbons, and my third bond is the double bond. I need 2 more carbons. Boom, boom. There we go. So there's 3-hexene. Carbons 2 and 5 have methyl branches. Methyl branches are just 1 carbon each. So there's a methyl branch on carbon 2, and there's a methyl branch on carbon 5. There's my molecule. Let's do one more of these together. How about part E, a little scary one. 2,2-dichloro, 5-ethyl, 6-fluoro, 3-octene. So there's a very long, complicated name. But let's just jump in and try it. So octene, 8 carbons with a double bond, and the double bond is the third bond in the molecule. So again, I'll draw the double bond. Has to be the third bond, so let me do this. It's now the third bond from the left. I've used 1, 2, 3, 4 carbons. I need 4 more. So 1, 2, 3, 4. There's my 3-octene. The rest of it, we can just start at the beginning. 2,2-dichloro. Chloro means there's a chlorine atom attached as a branch. 2,2-dichloro is telling me carbon 2 has 2 chlorine atoms attached. Carbon 5 has an ethyl branch. 1, 2, 3, 4, 5, and an ethyl branch is 2 carbons long. Carbon 6 has a fluoro branch. Fluoro would be fluorine, so I'll put an F there. So there's my 2,2-dichloro, 5-ethyl, 6-fluoro, 3-octene. What's its chemical formula? Now let's be careful about this because there's halogens in here. So octene has 8 carbons. The ethyl gives me 2 more. So there's 10 carbons in here. It's an alkene, so normally I would think it should have 20 hydrogens. But it's got 3 halogens, 2 chlorines and a fluorine. In order to put on a chlorine or a fluorine, you have to take away a hydrogen. So in this case, we'd have to take away 3 hydrogens, 2 for the chlorines and 1 for the fluorine. So if the molecule would have been C10H20, now it's going to be C10H17. We have to take away 3 hydrogens. Then we have to add the chlorines and the fluorines. I don't think it really matters which order you put them in. I'll put them in the order they were in the name. So the chlorines came first, so I'll say Cl2, and then the fluorine came last. I'm saying Cl2 because it was dichloro. This has nothing to do with Hofbrinkel because this is not the element chlorine by itself. It's chlorine attached to a hydrocarbon. So Hofbrinkel, the idea that elements are H2 and O2 and F2, this has nothing to do with the formula of hydrocarbons. So don't even think about that. All right, I'll leave you to finish there. Now, question 6, if you flip ahead to that, is a little bit more complicated. It's showing us this big, ugly organic molecule. It says that this molecule is beta-carotene. It's the pigment that's found in carrots and in several different kinds of vegetables. You look at the molecule and you can see it's full of carbons and hydrogens. I see rings, I see double bonds. It's a very complicated molecule. Part A says, based on the structure, would you predict this to be soluble in water? Well, it's full of carbons and hydrogens, so it's purely a hydrocarbon. That means it's a nonpolar molecule, and my answer to that would be no. If it's a hydrocarbon, it's only made of carbon and hydrogen, then it's nonpolar. Water is polar, so a polar solvent will not dissolve nonpolar solutes. So beta-carotene should not be very soluble in water. For part B, we're reminded that for each double bond or for each ring, we lose 2 hydrogen atoms from the alkane general formula. So what would be the formula for beta-carotene? Look at the molecule and count how many carbon atoms you see. Pause the video if you have to. How many carbon atoms are in that molecule? Okay, I'll count pretty quickly here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. There are 40 carbons in that molecule. So let's begin a chemical formula. C40, H something. Now, if this were an alkane, I'm going to write this on the side here, how many hydrogens would you expect? if it were an alkane. Well, for alkanes, we double the carbons and we add 2. So if there were 40 carbons, there should be 82 hydrogens in the molecule. But for every double bond, you lose 2 hydrogens. For every ring, you lose 2 hydrogens. Looking back at that molecule, how many rings do you see? Well, the rings are kind of easy. There's 2 of them. There's one on the far left and there's one on the far right. So we have 2 rings. So let me show that here. Rings times 2. For each of those rings, we're going to lose 2 hydrogens. So therefore, we're going to lose 4 hydrogens total as a result of those rings. Now, what about double bonds? For each double bond, we also lose 2 hydrogens. So how many double bonds do you see in that molecule? Stop and pause and count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 double bonds in there. So therefore, 11 times 2, we're going to lose 22 hydrogens because of the double bonds. So based on this, 82 minus 22 would be 60, and then minus 4, there should be 56 hydrogens in the molecule. Its formula C40H56. Question 7 talks about the cracking and the refining of oil. I'll leave you to do that. Question 8 talks about plastics and polymers. I'll leave you to read that. This is stuff you're going to be tested on, so be sure you read it and understand it, maybe even take some notes. This question in part C, you're going to use the internet, find some everyday examples of different types of polymers that you encounter in your life. Question 9 and 10 are also important to read and understand. Question 11 is related to that. Question 12, I'll leave you to do as well, combustion reactions for these different molecules. Question 13, we're going to look at alkynes really quick. So alkynes, we're going to try to name some of these molecules. So we notice the alkynes have triple bonds, right? That's why they're alkynes. This first example has 3 carbons, and so its name will be propyne. Just like propene, we don't need to say which bond is the triple bond because there's only 2 bonds present. Whichever one is the triple bond would be considered the first bond. So propyne is a sufficient name. In the next example, it's a bit more complicated. Find your parent chain. 1, 2, 3, 4. So 4 carbons. I see the triple bond, so I realize it's an alkyne. With 4 carbons, it's going to be butyne. But the triple bond with 4 carbons could be in more than one place. So now, just like with the alkenes, we're going to have to say which bond is the triple bond. And just like in alkenes, we'll number from the end closest to the triple bond. So the first bond is the triple bond. So the UPAC way of naming the parent chain would be but-1-ine. The Americans would say 1-butyne. But we also noticed it had a branch, a methyl branch, and numbering from the left, that methyl branch is on the 3rd carbon. So therefore, its name is actually 3-methyl-but-1-ine. What's its chemical formula? Well, it has 5 carbons. The butyne has 4 carbons plus the methyl, so 5 carbons. We remember that for an alkyne, the general formula was CnH2n minus 2. We have to lose 4 hydrogens from the original alkane formula because the triple bond has 2 extra bonds. So instead of C5H12, what it would be for an alkane, it's going to be C5H8. 2 times 5 is 10, take away 2, so C5H8. You can stop and count the hydrogens if you like to prove to yourself that that's correct. The next molecule, find the parent chain and make sure, just like we talked about for alkenes, that you include the triple bond in the parent chain. 1, 2, 3, 4, 5. So there's my parent chain. The triple bond tells me it's an alkyne, and it's near the right-hand side of the molecule. So I'm going to number from the right-hand side. It's the first bond in the molecule. Looking at branches, there's 2 branches. There's a methyl on the 3rd carbon, numbering again from the right-hand side, and there's a methyl on the 4th carbon, numbering from the right-hand side. So therefore, this molecule's name would be 3,4-dimethyl. Don't forget the prefix di. And then with 5 carbons, we'll say pent, and then 1-ine. And again, an American name would be 3,4-dimethyl, 1-pentyne. Let's do one more of these. Oh, how about G? Now for G, let me make it a little bit more complicated. In the molecule, let's add a bromine atom here, and let's add an iodine atom here, just to make it a bit more complicated. So let's find the parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a way to show the parent chain. People are sometimes confused with the triple bond, how to interpret the carbons. There's a carbon on each side of the triple bond, so keep that in mind. The triple bond has 2 carbons, 1 at each side. So there's 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5, 6, 7, 8, 9 carbons in the parent chain. This is an alkyne, so it's going to end in "ine" in its name. Which end should we number from? Well, let's check. Count the bonds. If I count from the left, the first bond, the second bond, the third bond, the fourth bond, it would be the 5th bond. If I count from the right, 1, 2, 3, it'll be the 4th bond. So that's where I'll count from the right-hand side. So the bond will be on the 4th bond. It's got branches, so let me grab a different color. There's a branch on the 2nd carbon, there's a branch on the 3rd carbon, 4, 5, there's a branch on the 6th carbon, and there's a branch on the 7th carbon. When you name branches, you name them alphabetically. The branches are iodo, ethyl, bromo, and methyl. So we're going to name those alphabetically. So here we go. The first one's going to be bromo. So we're going to say 3-bromo. Alphabetically, the next one will be ethyl. So we'll say 6-ethyl. Alphabetically, iodo comes next. So 7-iodo. And then methyl comes last. 2-methyl. And then this thing had 9 carbons, so none. And then it was an alkyne, and it was the 4th bond that was the triple bond. So non-4-ine would be its full name. What's its chemical formula? Well, nonine has 9 carbons. The methyl gives us 10 carbons. The ethyl gives us 12 carbons, so C12. How many H's would we have? Well, an alkyne would be 2n minus 2. So 12 times 2 is 24. Take away 2 is 22. But wait, we have two halogens, the iodine and the bromine. So instead of 22, we're only going to have 20 hydrogens. Each of those halogens replaces a hydrogen. And then the halogens can go in any order, but I'll do them in the order we put them in the name. I'll put bromine followed by iodine. Okay? So there we've covered some basic examples of how to do alkenes and alkynes. But I notice as I'm ending this video that I actually didn't talk about cis or trans isomerism. So I'm going to do that in a separate video because this one's getting a bit long and my dinner's arriving. So I'm going to stop here.